Hi, my name is Phoomiphat Kittisuphat. Today I'm going to present about the zero knowledge proof and the combination of it with blockchain and AI. So let's get started. So have you ever heard or familiar with these two codes, which is proving something is true without revealing the thing we are proving, or revealing the secret without revealing absolutely anything about the secret. So imagine a world where you can reveal a secret without disclosing a single detail about the secret, like picture proving the truth of something without ever unveiling the very thing you are proving. So this concept is the essence of the thing I want to present today, which is zero knowledge proofs. So let's get deep into it. So what actually is zero knowledge proof? A zero knowledge proof is a cryptographic marvel that reshapes how we approach privacy and security in the digital era. So, in this presentation, we will explore the fascinating intersection of zero knowledge proof and the combination of blockchain and AI to unlock the power to validate information without compromising any confidentiality at all. So, let's see how the zero knowledge proof work. So zero knowledge proof allow for proving the truth of a statement without revealing the statement itself or the method to use to discover the truth. So the proof is based on the algorithms that takes the data, some data as an input and output them like either true or false, just that. So the key criteria of the zero knowledge proof are three of them, which are completeness, soundness, and the zero knowledge. So first of all, the completeness. The completeness will ensure that if the input is valid, the proof will always return true. Soundness will guarantee that it is nearly impossible for a dishonest prover to convince an honest verifier that an invalid statement is true. Last one, zero knowledge means that the verifier learns nothing about the statement beyond its validity. So zero knowledge proof typically involve another three elements, which are witness, challenge, and response. First of all, the witness. The witness is the hidden information or the secret that the prover wants to prove the knowledge of. The prover. The prover randomly selects a question or a challenge related to the witness and calculates the answer and send it to the verifier. The verifier will randomly select an additional questions to ask, and the prover will provide the correct answers. So by repeating this intersection multiple times, the verifier will gain some confidence in the prover's knowledge without learning anything about the witness or the secret data at all. So let's see the example of the zero knowledge proof. So like assume you have a friend, like his name is Ronaldo, who is colorblind, cannot distinguish between color, which in this example will be the green ball and the red ball. So to him, the ball appears to be the same color because he is colorblind, and you want to demonstrate their differences. So he only needs to know if they are different, but not which is green or which is red ball. So next, you will give him the ball and take a note which ball is in which hand. Ronaldo will take the ball and put the ball behind his back and decides whether or not he will switch them. So after that, he will demonstrate them to you again after he switch or may not switch, and you must tell him whether or not that the ball have changed hands. So if you're not colorblind, you can do it very easily to distinguish between colors. So you can detect when the red ball was transferred from his left hand to right hand, for example. In fact, we can detect this with 100% accuracy because of you are not colorblind. But hold on, Ronaldo suspect that you might attempting to fool him So the ball appears to be identical to him. So he won't know if it is switch, if it is not the same color or not. So after all, we have 1 in 2 probability of accurately predicting whether he exchanged the ball or not. So those are pretty good odds, 1 over 2. So you decide to repeat the experiment again to prove that you are not colorblind. So your friend will cover the ball behind his back again, and the same, he will choose that he will switch the ball or may not switch the ball, and returns them to you. So again, you can see right immediately if he switched them or not, right? But however, if the balls are the same color, you have to guess again. And your odds of guessing it right have been cut in half. So you now have like 1 over 4 or 25% of guessing it correctly if you are guessing. So if you repeat this method like 10 times, your chance of guessing it right will decline to 0.09%. So the probability now is pretty modest enough to persuade your buddy, which is Ronaldo, that the balls are actually different colors. You can't just not be that lucky to be like lucky. But of course, you could keep going if you want to do so. So the chance of cheating lowers and lower in each repetition of the operation. So we have proven to our friend that the balls are different colors. So however, this proof does not really reveal the exact colors of the balls to our friend. So as a result, it was given the term of zero knowledge. So it's worth noting that a zero knowledge proof does not result in an anti-proof. So it's more like about the reducing the probability that someone is lying to you, but you can make the probability to be very very tiny, but very near zero, but it will never approach zero. So there are two forms of the zero knowledge proof, which are the interactive and the non-interactive. So the example or the illustration of you and your friend using the color ball that I just mentioned about is the interactive example of the zero knowledge proof. So as a prover, you had to take a sequence of acts to persuade your friend, the verifier, of a certain truth. So I think it's more like an interrogation. Like however, this approach has one drawback, which are which is the proof transferability, which is limited. So that is a drawback of the interactive one. So we convince our friend that the balls have a different color, but if we want to do the same with someone else who's also colorblind, we have to like repeat the entire process again and again with everyone. So that's a waste of time, right? So I would like to introduce you another form, which is the non-interactive, and allows you to deliver a proof. It will allow you to deliver a proof that anyone can verify by themselves. So you not need to juggle the ball around again like the interactive one. So in fact, you might have heard about the case knocks, which is used by some cryptocurrencies to protect the privacy of their user actually. So you see the traditional projects like the Bitcoin makes all the transaction public, meaning everyone can see everyone's balance and how they spend their coins. So, but there are also some other projects like the Zcash that use a non-interactive zero-knowledge proof to hide all of this. That's where the SNRK or SNARKs come in, which is short from the succinct non-interactive arguments of knowledge. So there is a non-interactive in the word. Okay. So for blockchains, we have to use a non-interactive proof because transactions have to be verifiable by every node on the network. That's how blockchain reach consensus. But It will be very time consuming to prove our transactions to every node on the network, but that's a neat application of zero knowledge proof. So aside from the cryptocurrencies, traditional banks could also make use of that technology of this technology as well. So for example, there is a Dutch bank named ING has built a variation of the concept called zero knowledge range proof. So this system designed to prove that a number is within a given range without revealing the actual number. So the blockchain of ING team notes that this can be used, for instance, to verify if your salary is sufficient to get a loan without actually revealing how much you make or your balance. Now, of course, you have to pick a large enough range, otherwise you can't actually guess the real number, and then it's not a zero knowledge proof anymore. So techniques like this could allow the financial world to embrace the blockchain technology. So right now that's a very tricky for them because they have to meet a lot of regulatory requirements, especially concerning about the privacy of their customer. So with this issue solved, we could see more banks adopting blockchain technology quickly, which could make their processes faster, more efficient, and perhaps even cheaper. So because of that, we can limit on how much information a certain company has on us, while the company has just enough information to offer you as a service or to comply with the regulations. So let's talk about how it related to AI. So building trust in AI with zero knowledge proof. So as AI models proliferate, especially those provided as a service via API, concerns about how businesses and consumer user can verify the accuracy of the predictions or the classification this system provide will grow. So how can a user, for instance, be convinced that a model has run correctly and without any error or manipulations? So as the regulators grapple with the implications of different forms of AI, it is also probable that in the future, regulators across different industries may also be interested in how to ensure trust in the use of the artificial intelligence or AI. While there are, of course, various mechanisms that can be used, it's interesting to consider whether there can be private sector, decentralized solutions that give the user of AI assurance without the need for heavy regulations or the supervision or supervisor. So, how can the provider of an AI model give the model confidence to the customer? So you might think of, okay, you can I can give the model weight that I trained for like a years or a century with pushing a lot of work into it. So you really going to give them to ensure your work that it really works. So if you really giving them your model weight to the customer, you have to face the leakage of your model weight. And another thing is that even though you give the model weight, the customer won't have enough that large scale of the computing capacity to train to use the model and work on it. So I don't think giving the model weight is the thing that we should do to build trust in AI yeah. So I'm giving you another uh, way to do it, which is using the zero knowledge proof. So first, every weight in the AI model is hashed by the model's provider. So they release this hash into the public domain, putting it on a third-party website or a decentralized ledger or somewhere similar. A provider may offer several models such as the premium model or a standard model, each of which would have a different weight and hence a distinct hash that would be released after the model's description. So next, a user would like communicate with the model provider if they want to test or use a specific AI model. Third, in order for the model supplier to apply the model to test the data, they would send it some. This could be done through the API or another method like file transfer or emails. Fourth, following the standard procedure, the provider creates the output by applying the model to the sent data. But this alone won't really tell the user that the specified model was faithfully applied. So we'll go to the next one, which is the fifth. Therefore, the provider would create a set case NAC proof using some public, which is disclosed, and some private, which is non-disclosed input. A set case NAC will generate a proof that can show the relationship between the value without disclosing the private input. So the weight in this instance would be the private input. The model's input and the output that were made available to the public would be considered public inputs. So after that, the provider will return the output together with a set case NAC proof, confirming that the model was executed correctly. For example, the model generates this output for the input that are provided given the weights, which are kept secret, and the common hash. Second, by using the test set to validate the set case NAC, the user can ensure that the model ran through without requiring the model provider to supply the model weight anymore. So the model provider don't have to get risk of leaking the model weight or put the model weight for the customer to use a large scale computer to test it. So there have been a number of explorations of this approach, including the open source project like the ZKML project, which demonstrated the effectiveness of this approach to the well-known MNIST image classification problem. And there are also many more projects that work on this. So another example with the AI could be like the credit scoring, which is one of the applications where this may be used in more detail in an ideal world. Every member of a population would receive the same score based on objective traits, devoid of the bias or the discrimination. With every classification, a credit score system might additionally offer zero knowledge proof, ensuring that the population has been using the same model as indicated by the hash. The hash. Obviously, this does not completely resolve the trust problem with the AI or with any other type of the third-party computing for that matter. Although it helps us guarantee the authenticity and the integrity of a model to some extent, it doesn't always address some of the more pressing issues that arise when we think about decentralized inference or model training, where the data may have varied pedigrees. So I would like to recap this thing again, that the zero knowledge proof, again, this the probability that the proof is fake can be very, very low, but it will never reach zero. So we can only use it to like increase the integrity and the authenticity, but it cannot be entering like 100% guarantee that it is authenticated. So yeah, it's just helping to increase the integrity, but you can use it to guarantee it won't be 100% sure. Yeah, because the probability of it to be fake will never reach zero. It can be very small, but it will never reach zero. So I think that's all for today. So thank you for listening. Hope you enjoy your life today. So thank you.